Cool. So let's talk about angular momentum. Angular momentum is, we've talked a little bit about how angular speed has a direction. And how did we determine the direction? Right, if something's rotating, which way does the vector point for angular velocity? How do we do that?
Is it tangential direction?
Not quite tangential. We use something called the right-hand rule, right? So remember, we had that bicycle wheel. Let me go grab it. This thing, right? If you just hold this and I drop it, what happens?
Fall.
It just falls, okay? But if we spin it and we give it angular momentum, right, and therefore an angular speed, hopefully I could spin it fast enough, and then I let go now, what's going to happen? It stays up, okay? So that tells us the vector actually exists. It points out, and we end up with angular momentum, which goes in the same direction as angular velocity, okay? So remember, momentum was what? How do we define momentum? Mass times velocity, and the momentum points in the same direction as the velocity vector, okay? Angular momentum, our rotational equivalent of mass, is going to be moment of inertia, okay? Our rotational equivalent of velocity is going to be angular velocity. So this is our new definition for the angular momentum, okay? Very stupid units of kilograms meter squared per second, okay? And that's just the way it is. Some of these units suck. But it's very much like mass times velocity, but it's just the rotational version of this, okay? And we can go back and forth between angular and linear momentum, just like we can go back and forth between angular and linear energy. And so we can combine these rotational problems with linear problems, and I'll show you how we do that in a little bit. But first, we're going to try that out. Okay, so we have a CD. Do you guys remember what CDs are?
Mm-hmm.
Several of you? Okay, so we have a CD, and it's spinning at 4,000 RPM in the clockwise direction, okay? Now, clockwise, positive or negative?
Negative.
Negative. Okay, so that we'll call that a negative angular speed or angular velocity, and we're obviously going to have to convert from frequency to angular velocity, and we want to know what the angular momentum is, okay? So we'll start with our conversion. Remember, omega, which is our angular speed, is just 2 pi times our frequency, okay? So when we plug this in, this gives us 2 pi times 4,000 revolutions per second. But of course, we know for every 60 seconds, sorry, revolutions per minute. Whoops. Minute. That's what the M stands for in RPM. And for every 1 minute, we have 60 seconds, okay? And that's going to give us an angular speed of 419 radians per second, okay? If we want to figure out the angular momentum, remember angular momentum is I times omega, where this is a vector. So there's one other thing we need to calculate, and what is that? Moment of inertia, which is I. We know this is for a disk, so we're going to have 1/2 mr squared. Okay, and that's going to be 1/2 50 grams. What is that in kilograms?
0.5?
Yeah, 0.05 kilograms, and the radius is 6 centimeters, so 0.06 meters, that's squared, and that's going to give us a moment of inertia of something very small, 9 times 10 to the negative 5th kilograms meters per second. Okay, meters squared per second. Where's the seconds? Kilograms per meter squared. Yeah, not seconds. Kilograms meter squared. Okay, then you plug this in. So we have 9 times 10 to the negative 5th kilograms meters squared times 419 radians per second. And that's going to give us 3.77 times 10 to the negative 2, so 0.0377 kilograms meters squared per second. So this is our angular momentum. And which way is it pointing?
Negative.
Yeah, also negative. So the whole thing should be negative. But that's only if we've defined a coordinate system, but it should be in the direction parallel to the axis. Okay. So we're just plugging these in. So in order to calculate angular momentum, you need to know angular velocity and also the moment of inertia of your object. Okay, and just to answer an earlier question that I saw in the chat, you do not need to memorize any of the standard angular moments of inertia, the ones that you would see in that chart that we showed. So if it's like a disk, a sphere, or something regular, you don't need to memorize those. Those will be given to you in a test situation. But if it's off axis, like not at the center of mass or not at the edge, like the ones in the chart are, then you can use the parallel axis theorem. And if you get something that's not a standard shape, you'll have to integrate it. Okay, I probably won't make you do that for this class. We'll just do it as an exercise. It won't be on an exam, but it is something that you could potentially need to know how to do at some point in the future. All right, any questions? So remember, if we have a particle, if we have something that's moving straight in a line, it can also have angular momentum, and that's a little bit complicated, but the reason we want to do this is if we have things moving linearly that also connect with things that rotate, okay? So what this means is if you want to convert from linear to angular momentum, you just take a cross product with the distance. And a way this might be useful is, let's say you have like a bullet, right? And you shoot it at the door. So let's say the door is like here. If you hit the door with a bullet, you'll cause the door to rotate, right? It's a collision, but this is a fixed object that can rotate. So you want to be able to go back and forth between linear and angular momentum. So treating the bullet as something with linear momentum and then using a cross product where r is going to be the distance from the hinge, just like we use for torque, allows us to go back and forth between the linear and angular momentum. So when we talk about r, that's just going to be the distance from any pivot point of an object that can rotate. Okay, so you'll have something with a linear momentum. It'll interact with something that can rotate, and so your r is going to be that distance to the pivot point. Okay, and so yeah, this is points from a point about which L is measured, right? So we're the rotational axis to the particle. So in the case of shooting the door with a bullet, it would be from the hinge to the bullet. Okay, that would be your r. This is your linear momentum, so mass times velocity of the bullet, and the angular momentum would be used for a conservation of angular momentum problem where you include both the bullet and the door as objects. Okay, this just restates the same thing. So if you call this angle beta, that's the angle, so if this is our linear momentum, that's our r. The angle beta is the angle between those two vectors. Okay, so it's just saying it's a cross product essentially. This is basically the same drawing in case this makes more sense. I don't know. There's two different versions of this slide, but we're gonna try it out by actually giving an example. And the example is we have a ball of clay that's thrown in from the right at 10 meters per second tangent to the top edge. So it's coming in from this direction, from the top edge of this disk that spins at a frequency of 1 revolution per second. Okay, so there's a lot of drawing that needs to happen so that you can get the signs right here. And we want to know the angular momentum of the system. Okay, we're not actually finding a before and after, we're just adding up the angular momentums. So there's 1 for the clay and 1 for the wheel. Okay, so let me set this up. Cool. Okay, so the first thing we want to do is draw this out. So we know that we have a wheel. We're gonna put it here. Okay, let's see. Okay, so which way is this turning? counterclockwise. So we know that it's going this way. We'll call that omega. It's not quite what omega is because that's going to be a vector pointing out of the screen, but that's harder to draw. And we have a ball of clay moving this way, and it's tangent. So for instance, here's our line. Okay, so we see this thing, it's coming in tangent at a speed of 10 meters per second. We have this disk, which has a radius of 0.15 meters. And then we know that it's spinning at a frequency of 1 revolution per second. Okay, so we want to know the total angular momentum of the system, which means we're going to find the angular momentum of the spinning disk and then also the angular momentum of the clay. So we'll start with the disk. So L is equal to I omega. This is for our disk. Okay, and I is going to be 1/2 mr squared, and then our omega is gonna have to come from this frequency. So that becomes 1/2. The mass is 2 kilograms. R is 0.15 meters squared, and this becomes 2 pi times the frequency of 1 revolution per second. Do we need to convert our frequency in this case? No, because it's already in seconds, okay? So when we plug all those things in, we get 0.075 kilograms meters squared per second. And then we also want to calculate the clay. So the moment of inertia for the clay is going to be the cross product of R and the actual momentum. What's the angle between those two vectors?
90 degrees.
Yeah, because when we actually have this collision over here, right, this thing's gonna stick up here. We'll end up with an R that looks like this, and we'll have a velocity that looks like this. Okay, so this angle is 90 degrees, and we can just drop this. So it ends up being momentum, which is mv, right, times r, which is just the same r as before. So we say m is still, let's see, what's the 0.05 kilograms. That's the mass for the clay. Our velocity is 10 meters per second, and our r is 0.15 meters. So you plug all that in and you get 0.141 kilograms meters squared per second. The only other thing to remember is these things, are they positive or negative? They're all positive, right? Because they're all rotating things in the counterclockwise direction, so we don't have to worry that much about sign. So our total angular momentum is going to be L disk plus L clay. We're just summing them up. 0.075 plus 0.141. All of this is kilograms meters squared per second. And when we sum these up, we end up with 0.216. And that's positive. Okay. So we're just adding up momentums. It's just like what we were doing before. Each object has its own momentum. You calculate them and add them up. It's just a little bit more complicated to calculate angular momentum than it is to calculate linear momentum. Okay. We'll try another one of these where we actually solve a problem. So in this case, we have a merry-go-round. It's a 250 kilogram merry-go-round, so it's a pretty serious merry-go-round. It's spinning at 20 RPM. This guy, John, runs tangent to the merry-go-round at 5 meters per second in the opposite direction than the way it's turning, okay? So he's is he speeding it up or slowing it down?
Slowing it down.
Slowing it down, okay? And then he jumps onto the outer edge. His mass is 30 kilograms, and we want to know the final angular velocity, okay? So if we want to draw, I'll draw this out, and then I'll give you a couple seconds to go over it. But basically you have a similar thing to what we were looking at before, but this time, let's say the merry-go-round is spinning in the clockwise direction, okay? And then there's a guy over here running tangent to the merry-go-round. And he has an initial speed here, okay? So we'll label the merry-go-round as having a big mass, big M mass, and then John will have little m mass, and then the merry-go-round has a radius of 1.5 meters. Okay, so try to set this up, and we'll go over it in a minute or two. So what do we need to do this problem?
That's a good strategy.
Where do we start?
Just
While I finish my Twix. I'm just gonna stare at you until you tell me how to start.
I start by getting the frequency of the merry-go-round.
Okay.
And then taking that and then getting angular velocity from 2 pi frequency, which was 2 pi over 3 radians per second.
Okay. So you know we're using conservation of angular momentum. So that means angular it's blue. Angular momentum initial is gonna be equal to angular momentum final. Our initial angular momentum is, there's two things, right? There's the merry-go-round, and then there's John. Okay, so those are, yeah, John. The merry-go-round and John. And then L final is just the merry-go-round plus John, because they become one. What kind of collision is this? Big one. Inelastic, yes. A good collision. Because John gets to ride a merry-go-round at the end, and that's sweet. Okay, so for the merry-go-round, we have I omega. And John is so MV and R. So mass, velocity, and R. Okay. The other thing we want to remember is, and then the final is still going to be I omega, but I is going to be a little bit complicated, so we'll talk about that in a minute. But I initial is just the merry-go-round, and then this is the initial angular velocity. So in this case we're gonna call the merry-go-round negative. And why are we calling it negative?
Because going clockwise.
It's going clockwise, right? So that's going to be negative 1/2 m r squared omega plus little m v r is equal to, now once these two things become one thing, let me see. Oh no. Okay. At this later time, we have John on the merry-go-round. Okay, so how do we calculate the moment of inertia here? What do we do if we have more than one moment of inertia that are working together? Yeah, you just add them up. It's actually surprisingly simple. So our final moment of inertia is going to be I merry-go-round plus I, John. And remember, what's the moment of inertia for just a point? Let's treat John as a point. What?
Is it 1 mr squared?
Yeah, it's just mr squared. So this is going to be 1/2 mr squared plus little m r squared. And why are we using the same r here? Yeah, because he's at the edge, right? So we can use the same r. Okay, so then this becomes 1/2 mr squared plus mr squared times omega final. Okay, so there's a lot going on here, but we're just going to solve for omega final. If you want to plug these in independently, I believe that the merry-go-round is 598 kilograms meters squared per second. Yeah. The John starts with 225, just if you want to check your answers, kilograms meters squared per second, and then the final angular momentum is 349. So once you add those together. I'm going to just solve for omega final, which is going to be mvr minus 1/2 mr squared omega divided by 1/2 mr squared plus little m r squared. Okay? Yeah, that should be good. We plug these in. This becomes, well, you can plug in these numbers. So this is 225 minus 589 divided by, what is it, 349? I'm leaving off units because we've already had a rough day. But it gives us 1.04 radians per second. Did anybody get that?
That's something kind of around there.
What'd you get?
1.16.
It's good enough. It's one-ish. One-ish radians per second. All right. Any questions about this? Yes.
So to get the angular velocity at the end, you just divide by the total mass of the system?
The total moment of inertia of the system. Yeah. So you'll end up getting your total angular momentum, and then you divide it by the moment of inertia of the whole system, the John plus merry-go-round system. Yeah. The only other thing to be careful of is this negative sign, because you know that he's slowing it down instead of speeding it up. Okay. All right.